input state section represent the possible inputs we provide to the system, and the output section simply gives the output of the corresponding inputs. So here's the state diagram. So simply the state diagram is the graphical representation of the information present in the state table. Like if the present state of the system is 0, 0, and we give the input 0, it will the next state of the system will remain as 0, 0, and the output will be 0. So this is input of this input, and output, and the second one is output. We write after the slash, so output. So this is the present state, and write inside the circle, and we denote the next state with that arrow. So for example, if the state is 0, 0, we give input 0, the output will be 0, and the next state of the system will be 0, 0. If we give input 0, the next state will be 0, 1, and the output will be 0. So similarly for this one, we can see if we give the input 1, the next state of the system will be 1, 0, and the output will be 0. And if we give the input 0, the output will be 1, and the next state of the system will be 0, 0. So yeah, we can see like that. So here are some examples. This is of our state table. So if the present state of the circuit is 0, 0, we give input 0, the next state will be 0, 0. If the present state of the circuit is 0, 0, we give input 1, the next state will be 0, 1, and the output will be 0. So similarly, we can write it in this way also. Here we are just reducing the number of columns, number of rows. So here, if we give the input 0, 0, if the state of the circuit is 0, 0, and we give the input 0, the next state will be 0, 0. If we give the input 1, the next state will be 0, 1. So similar things you can write in any of these ways. And this is the state diagram for corresponding state table. So yeah. So state reduction and the state assignment. So the state reduction is reducing the number of states by eliminating the equivalent state. So what is the equivalent state? If the input and the next state and the output of the output of any state is the same, so we call it as an equivalent state. So here you will not find any equivalent state. So we'll give example later. So and the state assignment, so we do it to reduce the number of flip-flop used in the circuit, as we used to do in combinational circuit using K-map. We used to solve the problems using K-map so that we can reduce the number of gates used to make the circuit. And the state assignment method is to assign some binary values to the state in such a way as to reduce the cost of the combinational circuits that drives the flip-flops. So here's an example. So let's say present states are A, B, C, D, E, F, G, and the next states are A, C, D, and these all. And these are the inputs, x is equals to 0 and x is equals to 1. These are the outputs. So here you can see if the present state is E, we provide the input 0, we are getting A, and we provide the input 1, we are getting F, and the outputs are 0 and 1. The similar thing is happening with the G. If we giving the input 0, we are getting state A, and if we are giving input 1, we are getting state F. So E, and same thing is with the outputs also. Here also it's 0, 1, and here also it's 0, 1. So the E and G states are equivalent. So we can remove any of these two. So as you can see here, we have removed the state G. And you can see for D and F also. For D, it is E for 0 and F for 1, and the outputs are 0 and 1. And for F, it is G. So as we have seen here, E and G are similar. So here it is E, so E and G will be similar, are equivalent. So E and G will be same. And here F, and here also F is 0, here 0, here 1 and 1. So we can remove any one of these D and F. So here we have removed the F and G. So we have A, B, C, D, E as the present state. So here we can Like that we can reduce the number of the states. So here designing the design procedure for the clocked sequential circuit. So firstly, you need to write the given description in the form of state diagram or the timing diagram, and then obtain the state table using the above state diagram or the timing diagram. And the number of states can be reduced by the state reduction, as we have seen earlier. And state assignment also can be used if it is required. And determine next step is determine the number of flip-flops required and assign a letter to each flip-flop. Choose the type of flip-flop to be used, derive the circuit excitation and output tables from the state table, obtain the expression for the circuit output and flip-flop input, and implement the circuit. So we'll see an example for that, then it will be clear. So let's say this is the state diagram and this is the state table we have given, and we need to make a circuit out of this. So we'll use the JK flip-flop. So this is the JK flip-flop, and this is the state table given. We have written it in this form. So this was the state table. We have just written it in state, present state, input, and the next state here. So we will derive how we are getting the inputs of the flip-flops. So here we are using two flip-flops. The one flip-flop is A and the second one is B. The JA and KA are the inputs of the A flip-flop, and the JB and KB are the inputs of the flip-flop B. So here we'll see. So we'll use the K-map for that. So this is the K-map, 3-order K-map. Here is writing A, and this is the BX. So we can see the function table for JK flip-flop. So if the present state is 0 and the next state is 0, so the input J will be 0. So if the present state is for A, we will see for the present state is 0 and the next state is 0, the input will be 0, 0. So here we will write 0. Here it will be excuse me. Here it will be 0, and here also it will be 0. So we have not written anything here. And for this, if the B and X is 1, 0, so you can see if the B is 1, if the B is this one. This one, B is 1 and X is 0, and the input is 0. Input is 0, and the next state is 1. We write it as 1. And the next state here it is 1, and the B is 1, and the input is 0, and the next state is 1. So when the present state is 0 and the next state is 1, J is 1. So here the present state is 0 and the next state is 1. So for that, we are getting Bx is equals to 0, so we will write 1. And if the Q is 1, 1, the J is don't care. So for all this 1, we will write don't care. So when we solve this K-map, we get it as J is equals to Bx. So that's what we have written here. If J is equals to Bx, and we can solve for Ka and Jb and Kp similarly like this only. So now we have the two models, Mealy and the Moore model. So in Mealy model of sequential circuits, outputs are the functions of both present state and the inputs. And while in the Moore model, the output are the function of the present state only. So in the Mealy model, the output of the circuit depends on the present state as well as the input. But in this Moore model, the outputs only depends on the present state only. It does not depend on the input. So you can see here the examples. So this is the Mealy model. So this is the Mealy model. Here the A, B, C, D, E, F, G, these all are the present state, and 0, and this is input, and the slash we have written the output. So this is the present state, and the next state, and the output, and X, this is the input. And the Moore model, it does not depend on the input, and we write output, we here write inside the circle we write the output of the circuit. So 0 0 is if the 0 0 we're getting 0, the next state will be 0 0. So, sorry. Yeah. Okay, so the main difference between Mealy model and the Muri model is that it in Muri model the output does not depend on the input we provide to the circuit, and the Mealy model the output depends on the present state of the circuit as well as the input of the circuit. So yeah, is uh, is everything clear? So yeah, we stop here, and Sandeepan, you can take over.
Yeah. Yeah, so coming back, just to give a brief overview of what Soumya said, like what is this state that we're talking about? What is 0001 and what the hell is this? Right. It's nothing but like take a flip flop. Like let there be two flip flops. Okay. So let this be flip flop A, let this be flip flop B. So the output of this flip flop, this is the state, right? Like if I have 00, then my state is 00, right? This is my state 00. If it's 01, then it's 01 and 10 and like that, so on and so forth. So let you have a machine, right, which has two flip flops. Let this be a box. Okay, the board. Let there be a box. Let this be a circuit. Okay, inside I have two flip flops. Flip flop A, flip flop B, right? And these are the output of my flip flops. Now this box can have an input X, okay, and say there's an output Y. Uh, okay, so I can have a few possibilities right now, right? I may have an input or I may not have an input. I may have an output or I may not have an output. So like say or my output may just be the state of the my output may just be the state, right? So my output can either be the state or my output can be a combination of, like inside this maybe let's say there's another box, right, where I'm taking in X and I'm taking in this state, right, and I'm getting in Y. Okay, so the output may either may be a combination of this or it may simply be the state. So if it is simply the state, right? If it is simply the state, then it is the moon model, right? And if it is this, right? If it includes this part, then it's called the Mealy model. Okay, so that, and so I'll just show another example. Okay, like this is the same circuit as the one above. Uh, Now we're implementing this using a T flip-flop. Okay, so and one more thing, like the one which I showed you. It may so happen that neither there's an input nor there's an output. Okay, it may happen that this is pre-programmed to go through a fixed number of states. Like say maybe initial state is 0 0, then there is 0 1, then there is like say 1 0, then 1 1, right? And then maybe it comes back to 0 0. So in this device, there is no input, neither is an output. Right? The output is simply the state. Okay, so this also may be a case. And this you can figure out what this exactly thing is. This thing is exactly what we call a counter, right? It counts from 0 to 3, from 0 up till 3 and then back to 0. So I'll be covering that now. So just before that, I'll just go through a quick example here. So again, the state diagram here is 0 0. Right, if my input is 0, then I remain in the state. If my input is 1, I just go here, right? And if my input here is 0, then I come here. If it's 1, I stay here and like that, so on. So to find the circuit for this diagram, right, what you do is simply first draw the state table, right? You take in the present input, you take the present state and input, find and write the next state and input from next state from here, right, from the diagram, and then you add this part, right? Then you add this column to it, right? And how do you find it out? Like this is the transition, right? This is a transition, and so if the state is same in my T0, right, for both of the individually, here this B flips right. only B is flipping, so my TV is 1, and so on and so forth. You can write down up till the end. So once you have this entire table, then you have to just find out TA and TB, right? TA and TB as a function of, like, say TA is equal to f of a function of a comma b, right, comma x. Okay, because it depends on the input, right? My output also depends on the input. For x, if x is 0 at the same state, if x changes, right, I have two different next states, as you can see. So it is a function of a comma b comma x. And so the best way to find out the answer is by using a k-map, obviously. And this is what you will be getting on putting the values. When t is 1, you put in those values for db and x, and you have this k-map, and solving you get these two expressions you get, right? And if you like, what will be the circuit for this thing? It will be nothing but uh, okay, I'll draw it here itself. Like for this flip-flop, right? uh, Two flip-flops there are a and b. Let this be a, right, and this be b. So this output is a basically, right, and this output is b. So let the input be x, right? So this combinational logic, this feeds to TA, right? This is my TA, right, and this is my TV, and this is my TV. So T is nothing but a dash b x dash and of these three. So I have a three input AND gate, right? One of them feeding in is a not, right? So this one, a bar feeds in here, another one b feeds in here, and the last one we have x feeding in here. So this combinational circuit comes in between here. Okay, I'm presenting as it is this box. So this is one input for this guy, another input for TB. You get the same expression you put in here, and that's how you find it. So if you simply clock that circuit, right, and change the inputs, then you can observe exactly this behavior that you're getting here, right? So I hope you understood something out of that. Now coming to counters, right? So as I've already given an intuition of what counters are, a counter is simply the same thing, other than the fact that there is no input and the output is just the states, right? So it's a register that goes to a prescribed sequence of states of an application of input pulses, right? Input is nothing but the clock. So what the counter does is, the counter will just count the number of clock cycles, right? Or maybe you're doing an interrupt, maybe you're pressing a button, right? So if you feed that in as the clock to the counter, then the count becomes +1. Okay, and so on and so forth. So now there are a lot of types of counters. Type number one is the asynchronous counter. So there are actually two broad classifications. One is asynchronous and one is synchronous. As the name suggests, asynchronous means that uh, direct. Okay. First to tell you that, then I have to show you what these counters are, right? So just remember, asynchronous counters are ripple counters, and I'll be coming to the examples below. And another part is synchronous counters, right? So I'll just show you, then you'll understand instead of reading to the slides. So a ripple counter basically is that, come down. Yeah. So this is the ripple counter, asynchronous counter. There are 4 flip-flops. I mean, whatever number of bits you have, right? Like, say I'm counting from up till 16, right? 15. So I'll need 4 bits for that, right? 0 to 0000 to uh, 1111, right? So I can do it in 4 bits, right? If I'm counting 16, then I need 5 bits. So as I already said, the output is nothing but the states, right? So for if I'm counting to 15 for 4 bits, then obviously I need 4 flip-flops, right? 1, 2, 3, 4. If I was counting up till 4, then I would have needed 2 flip-flops. Similarly, 3 flip-flops for up till 7, right? Uh, I mean, sorry, for if I was counting up till 3, then I would have had 2 flip-flops, right? 0001 1011. And so what this does is, why is it called asynchronous? Because if you notice the clock of each is different, right? uh, the output of this one is fed to the clock of this one, and so on and so forth. It's like cascading. Like the output of one goes as the clock of the second one, and similarly so on and so forth, right? If you notice, it's a synchronous connection. It's not a connection, okay? It's overlapping, right? You can take it off this part. So A1 is connected to C, right? 1 second. So if you notice, A0 is connected to C of this one, A1 connected to C of this one, and here the T's of all are connected as one, are connected to logic one. And what does T flip flop logic one do? It just toggles, right? So what this will basically do is, uh, just come up here. So let me take two flip flops, right, to show you what happens. Let them be T flip flops. Okay. So this is my count. I mean, using what it triggered on the circuit. Okay. I mean, what it should keep a track of. If I like say I have a button here, I have a push button here. Okay. If I click this button, my count should increase by one. So what happens is first, okay, and the output of this, let it be connected to the clock of this. So first what will happen is when I'm clicking on this button once, okay, then this gets toggled, right? Initially the outputs be zero of both the flip flops. Okay, initially let them be zero. So what happens is every time, just say every time I click on this, right? Every time I click on the button, this will toggle, right? This flip flop will toggle, will go between 0 to 1, right? So uh, okay, say the first time I'm clicking on it, this becomes 1. Okay, and let this be positively triggered. Okay, both of them, let all of the flip flops be positive edge triggered. So when I'm doing 0 to 1, this output goes from 0 to 1, right? So this gets triggered, right? Wait 1 second. I'll just make it. I'll just make it negative is triggered. Let it be negative is triggered for the moment, right? For you to understand. Otherwise, I have to change the voltage of this. So when I'm clicking on the button once, right? This gets triggered, right? This gets triggered, and I have an output of 1. And similarly, it goes on that then this will toggle, like this becomes 1, this becomes 0, and then this comes back to 1, right? During this transition, this gets triggered and this will become 1, right? Then the same, I mean, like if you look at your if you let me take a 3 bit truth table. Okay, that's easier to understand. 0 1 1 1 0 0 1 0 1 1 1 0 and triple 1. This bit, this column, right? If you notice in this entire column here, it toggles on every cycle, right? So this is equivalent to my first flip flop here. Okay, this column, second column, is equivalent to my second flip flop. Why? So if you notice that whenever this transition from 1 to 0, this toggles, right? So this is 0 0 for once, 1 1 0 0 and 1 1. So the frequency of this is exactly 1 by 2 of this what, of this first column, and same goes for the frequency of this one. The first 4 guys are same and the next 4 guys are same. So the frequency is 1 by 4. Time period is 1 by 4, so the frequency becomes 4f, right? 1 second. Let's see, times time period changes. Time period increases, right? Time period increases here, and so the frequency can decrease, right? So it is 1 by 4 only. Yeah. So my frequency is getting divided by 2 and after every stage, right? The next flip flop will have a frequency of f by 4. Sorry, 1 second. Time gets multiplied by 2, last frequency is divided by 4. That's fine. Yeah. So this is called a frequency divider circuit as well. So if you notice the output for this guy, there are 2 cycles at 0, then 2 cycles at 1, right? And then again comes down, 2 cycles at 0 and 2 cycles at 1. So time period is 2 times, right? So my frequency is f by 2 of the first one. Cool. And so on and so forth. The number of flip flops you keep on connecting in cascade, that number of times 2 to the power n, the output frequency will be. So coming back, I think you got why exactly this becomes a counter, right? Because the first flip flop will toggle 0 0 0 you have, right? 0 1 0 0 1 1 1 0 0 and 1 0 1 1 1 0 triple 1. So the first guy keeps toggling like this. Second guy keeps toggling at one half of the frequency, and the third guy gets toggling at this one, right? So this exact behavior, the state sequence is followed like this itself. If you notice, right? If you write down, if you keep on pressing the switch and you notice the outputs of all the three flops, then this is exactly the sequence which you'll get. Okay, so that's why I mean it counts from 0 to 2 to the power n, basically the number of flip flops you have connected in sequence. So so this one uses T flip flops, right? You can do the same thing using D flip flops. This circuit is a bit different. It's something that other than the fact that after again here it also you're toggling the output itself, right? For D, whatever you feed in as Q bar, that becomes the next state, right? So it's equivalent to toggling. So if you notice, the circuit is the same here. So at the end, I'll show you a demo of this exact thing. So don't worry, you'll understand what exactly it is if you haven't understood what I said. Now coming to synchronous counters, this is much simpler than the asynchronous counters, and it has less complicated gate timings. Why? Because everyone is getting fed with the same clock. That's the fundamental difference between them. Right here, the same clock is fed to all the flip flops. The arrangement is exactly same. Okay, for 3 bits, I will have three flip flops. Okay, and the state is my output, right? And it's just that now all the clocks are same, right? All are connected to the same clock. Right? How did this part come, right? Like that was connecting. Here you're simply connecting the outputs to each, right? For up counter, you were connecting this. For down counters, you're connecting this guy. So I'll show you that for you to understand exactly why this will count down as well later on. But at the moment, let's consider on this guy. Here the clock fed is same, but how did I get this part, right? Like it just can't come from anywhere. So if you notice, like the state diagrams of a what? The state diagrams of a flip flops that were connected to the same clock, right? सबका same clock था state diagram में. So the same thing I can write as a state diagram here, right? If you know, I did not represent this as a state diagram. I just reduced truth table for that, right? By simple observation. But here I'll be drawing the state diagram, and I can solve for these. I can solve. I can find this t inputs for all of these guys. Just as we did in the above example, right? So 0, 0, 0 to 0, 0, 1. This is a complete. It counts up till 7 and comes back to 0. So it counts up till 7 basically. Right? It has 8 states, so from 1 to 7, 0 to 7. So if you were to write this down again, you could write it down in the same form as here. Like you have three, like we'll also have an additional present state C, right? We'll have 0, 1, like that will toggle, right? And now your output will be this flip-flop input, right? This will be here again. You will have a C next, right? This will be a function. There will be a function of A, B, C, and if you notice in the counter we have no input, right? In the counter there is no input, so this will be a function of A, B, and C, right? So you get TA and you get TB. So that is there. Similarly, you can also find the circuit for a 4-bit flip flop that counts up till 15, right? 4-bit counter counts up to 15, right? So I guess that's done. I'll show a demo of this at the end also. Coming to ring counters, uh, like the one which we're using for the event mostly is the synchronous count itself. Okay, this is exactly what we'll be using in the entire event, and that too you don't have to know what exactly happens inside, right? We won't be asking you to implement a counter using a state diagram, but this will be given to you as a box, right? This will be given to as a box, and you'll be just a trigger, right? You can just have a trigger. There'll be a hold pin or there'll be a count up pin, okay, and one more pin for count up or count down, like +1 or -1, right? That. So coming to a ring counter, the ring counter is almost the same as shift counter. Just that, okay, this may not be visible to properly, but it's nothing but again 4 flip flops connected in series. Again, flip flops in series, right? The output of one feeds into the other one, and this the last output feeds back to this guy. Okay, so you might wonder what is the function, what is the use of this, right? So imagine my initial state is 0, 0, 0, 0. Okay, and you might also be wondering that this is a complete loop. Where is the input? Right, there's no input to any of the flip flops if you notice. So externally. So what am I doing here? So let's, like, if you remember in the last workshop we taught you that there are two extra pins to the flip flop, right? One is set, one is reset. So let this be the set pin, right? If I drive this pin, then my output becomes 1, right? So if I'm giving if I'm giving 5 volts to this pin, my output becomes +1 here, right, of the flip flop. So imagine I'm giving a short pulse and I drive the output to this to 1, right? So I'm having 1 0 0 0. Okay, externally I, then the next cycle what will happen is this thing will shift forward. This guy comes here and this right shifts. So I'll have 0 1 0 0, right? And then the next thing goes on and so forth. So after this I'll have next cycle I'll have 0 0 1 0, and then I'll have 0 0 0 1, right? And finally I'll be having again 1 0 0 0, right? So this is my ring counter, and the same thing has been denoted here. This guy feeds back into this, and you have that. So the applications of this are a bit different, to generate 4 timing signals of like the different at different times, right? So again, you won't be using this directly. It's just for you to have an intuition of how to drive, how to to get an idea of the following state sequences, right? Just for that. Another modification of this ring counter is the Johnson counter, and there is no difference between the two other than the fact that there I had disconnected, right? But here I have disconnected. I'm connecting Q04 to this. Okay, and that's the only difference. And that will reflect as if you notice the outputs here, you can see the change there. Like initially I'm feeding Q1 as 1, right? Then this 1 keeps shifting down, but only thing is here initially this output was 0, right? This output here was 0, so this was 1, right? So this 1 comes in back here. So one gets pushed in from this left. So next I'll have 1 1 0 0. Then again I'll have one push in 1 1 1 0, and like that you can write down till the bottom, right? So nothing much to explain there. Time for the demo. Like, so the main part of today's workshop was the counters, I can say, right? And that too not the entire thing, but just a part of it. Yeah. So this entire part I have shown you in the last workshop, right? So I'll just put it away for a while. Okay. And this is the part I wanted to show you now. I'll put lock in. I think this will still work. Yeah. So coming to them one by one, right? I have 5 circuits here. So these are two. So coming to the first one, this is a 74161, right? So if you type in what a 74161 is, then you'll see that it is a synchronous 4-bit binary counter, right? So as I told you that we will not be using asynchronous counters. You can design them by yourself, as I'll show you. But what we'll be using for the event is a synchronous 4-bit binary counter itself, right? We'll be using the 74161 itself. So what this does is, as you can see, I've fed in a clock, right? It's a label here, so like don't think that where is it? It is very much here, right? Just fed in the form of a label. Like see, there is a clock. So I have a clock in feeding in the clock, and these EP, NT, load and MR pins. You can check out the data sheet of this IC, right, and figure out why I've kept them as 1. Okay. The main thing to focus here is this 4 zeros, right, and the output here. So if I click on the play button, so as you see the clock pulse is going up, right, and it's counting from 1, 2, then 3, and it'll keep on up till 15. It will go, right, and notice what happens after that. Okay, 1 second. I connected the wrong video. Uh, Let's change the clock frequency. So 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. I will go back to 0. Yeah. So the internal circuit of this has that state diagram implemented itself, right? From 0 to 15 and then back to 0. If you notice here that you have no control over whether it can do count down as well, right? It just keeps on counting upwards. And what are these four zeros, you might ask, right? So that is the function of this load pin, right? So if I'm enabling the load pin, right, then whatever is inside here, say if I'm giving in 2, so my counting starts from 2. So if you see, first I'll have 2, and then I have to disable this load, right? And I'll start counting upwards, 3, 4, 5, and it'll go on, right? So that is all about that IC. Now coming to this one, this is a modification of the above one, right? This is a further advancement of that. In which form? Like in the form that this can add up as well as down, right? You can see this extra pin at U/D bar. Up for counting upwards, you have to keep this as 1, right? And for counting downwards, it has to be 0. So if you notice, if it's 1, it's counting upwards again, the same thing. And if it's down, okay, I'll count up to some part. 1, 2, 3, 4 maybe, and we'll come back to 3, 2, 1, and 0, right? And then we'll go back to 15, and so on and so forth. Okay, so it's connected in both ways. It's like a cycle. Okay, so and the same load pin has the same part here, LD. It has the same functionality here. It loads in the whatever value is given here. Okay, so you'll be using these two circuits itself, right? These two ICs only for your event, for both the events, DIGISIM and FUNCKIT. And now coming to the asynchronous counters, I've just drawn it out for you to have an idea, right? So if you notice, I'll just show what it does first. So you look at the outputs, right? This is my input, right? For asynchronous counter, as you remember that there was no clock, right? So one second, like there was no clock, right? So what I did was, what I have to do is to trigger it is I have to keep on pressing this button, right? So if I press this button, so I get 1, right? Then I get 2. Sorry, this clock is positively triggered, right? So every time it becomes 1, the count becomes added up plus 1, right? So 3. And and if you notice that, as I told you there, like this first guy will keep on toggling. The first output of this one is this one, right? This rightmost one is the output of this first one. So this keeps on toggling, right? The second guy toggles at every 4 times I click on this button, and the last one every 8 times I click on this one, right? So if you play with the circuit, then you can have a look at that, right? It counts up to 7 and then comes back to 0, right? So that is your asynchronous ripple counter using a JK flip or T flip, whatever you can use. And now the fun fact about that is, mm, yeah, a fun part about is this one. That's the answer counter. Yeah. So the fun fact about this one is that if you want to count down here, right? So this is for counting up. If you want to count down, just connect this Q to the clock, right? And if you see, it's counting down. 9, 4, 3, 2, 1, and 0. So why it is happening, I leave it to you to find out. Okay. And if I make this registers positive as negative as triggered, right? So the Q and Q bar thing will just swap for up and down counting. Okay. So that you will figure out yourself, I guess. If you watch the videos on NASA Academy, it is very well explained that why it happens. Okay. So I leave that to you to figure it out later on. Now coming to ring counter, right? This is a ring counter, right? The flip flops are put in connected together, and the output of the last flip flop is fed back to the first flip flop. So initially, as I told you, I have to trigger this set button, right? This set input. So if I make it 0 and 1, so I had 1 there. It happened very quickly, so I didn't notice. So it keeps on counting bits after that, right? So, so this is just going on. Whatever is here keeps feeds back in here, and the rest shifts, right? 0 1 1 1 0 1, and yeah, I guess you figured it out. So Johnson counter, same thing. I'll have Okay. Uh, 1 second. Yeah. So Johnson counter, what happens is instead the initially the output is zero, right? So Q bar is one. So one will come feeding in and one will start propagating to the right. So if you notice, one comes here first, then one comes here, one comes here, right? If I want to feed in zeros, right? So if I trigger this, so I can put in more than one once. So that I see. So that's the Johnson counter for you. Again, you won't be using them. You won't be using these two or these three. You will be only using these two guys. So with that, we come to the end of all the theory content for our workshops and for the event regarding digital electronics. The last workshop will be on PCB designing. Uh, now just want to tell you some tricks and tips and tricks about Proteus, right? What which you can use in your circuits. So uh, 1 second. So first, let me if you have any doubts regarding any theory. Then just unmute or write in the chat. Okay. So I figured I'll show you the last part itself. So as I said that you can change the initial output of a flip-flop, right? Uh, let's put this back in. Maybe. Okay. So I can change the initial of a flip-flop by doing edit properties. I can set the initial state to high also or low, whatever. So initially it is one, right? So that I can do. I can change the clock frequency as I showed you already. Then I can add labels, right? So like here I've added a label. So I'll just delete this. I'll show you how to add it once more. You have taken a label, right? You click on here and you type in whatever label you want, and then just given the same label to any here, any of the other pins when in any IC, and the same whatever comes in here gets feeded down here. Okay. So initial value done, label done. Yeah. Then coming to, you can copy and paste, right? So like maybe I have two sheets. Okay. Uh, I can move this as I showed you also. I can do a block copy. Okay, I can copy and put it here. Just the only thing is that, okay, wait, let it be. So I can copy. I can also copy between two sheets. Uh, like let me show you. I'll just open another Proteus instance. So I can copy this to clipboard and I can paste it there itself as well. Just one thing, be sure that the name also gets copied, right? So it may happen that you already have a circuit with the same name here. So there will be an error that Proteus will show you. So you just have to change the name of this guy. Okay. So that is that. One more thing, you can also, okay, so three things done. The last thing I have to show you is a sub-circuit, right? What is a sub-circuit? I guess I'll close this. Uh, Say maybe I'm implementing an 8-bit register. Okay, so I have two 74179s, right? So I'm making an 8-bit register, right? So I'll have to make it using two of them because there is actually no 8-bit register inbuilt, right? In Proteus. So I'll connect 8 numbers here and 8 there. But what if I want to make them together, put them as one piece? And say if I have a lot of circuits on the board, right? Say I have two resistors here, two more resistors here, and I can combine them as one, right? I do not want it to look so big and clumsy as the entire circuit here, right? Looks very clumsy, right? So sometimes to clear up the clutter on the sheet, this feature comes in very handy. It's called a sub-circuit, right? Click on ports. Okay, 1 second. Click on ports, right? And you draw a box simply. Then you go to child sheet, right click, go to child sheet, and then you put in whatever component you want here. Cool. Okay. Now how do you connect the parent sheet and the child sheet? Right, this is exactly same, right? How do you connect the two together? So for that you use this part, terminals. Terminals tab. Okay. For inputs you take an input, right? So connect inputs, and for output you take an outputs. So I'll just show you one, two, three inputs. Okay, I have to just remember I have to name them as well, right? So I have to give them terminal names. So I'm giving A1, A2 here, and A3 there, and output I'm giving as O1 and O2. So if I go to the parent sheet now, connect these as well, right? So if I go to the parent sheet now, so I'll have to add those terminals here as well, right? One second. I think it will be a port. Yeah, no, sorry. Has to be a terminal. Okay, terminal, input terminals. Yeah. So you click on this blue bar, right? And you can add these guys. Okay, and this should be an input one. I collected an output one to this. Okay, and these are my outputs, right? So again, I have to give a name to this guy. So A1, A2, and my outputs go as O1, O2, right? So now they get connected together. So my A1, A2, A3, and my O1, O2 get connected to my parent sheet. Okay, so now these guys get connected. If you are feeding in say logic states 1, whatever you feed in here, so that output goes there. Okay, so that is one thing. And what else is left? Okay, and the last and final thing from my side is a ROM, right? You'll be using a ROM in all the PS of DIGISIM, right? In both of them. So the ROM is 2732, which you'll be using. What does the ROM do? The ROM is nothing but it has 12 inputs, right? From A0 to A11, and these are connected to 0 1 normally. This is a standard input, right? It's connected to 0 1. This is my ROM. My output is an 8-bit number. Input is 12-bit, output is 8-bit, right? So this is nothing but uh, you can store data inside your ROM, right? It has you can store an array of numbers inside it, like 1, 2, 3, 4, 5. Okay. So how to store that array? So for that, I'll send you this sample code. Okay. So this exact code I'll send you. You have to change this, just change this array, right? Whatever numbers I put in this array, the same gets fed into the ROM one by one, right? You get this Python file, click on run, okay, and you generate this file, right? Wherever you run this program, you'll get this ps.bin, whatever name you put in, right? And that binary file you have to feed to this ROM. Right click, edit properties, click on this image file, and you feed in that. Okay. So I think I've done it here. So my ps.bin is here, right? And I fed it inside here. Now if I put in, say I'm putting in, so for 0 0, right, my output is, what is my output here? 1 plus 8 plus 16, right? 25. So if you notice that my first number was 25. Cool. So if I'm putting in 1, my output becomes 4. So 4 like that, and so on and so forth, right? So I can have a total how many numbers in my array? 2 to the power 12, right? And my output will be of 8 bits. So it will vary from 0 to 255. Okay. So sequentially, as you go on and go forth, you can basically loop through an array, right? Using a DOM. Okay. So in both the problem statements, we'll be using a DOM. And so I guess that is it from my side. I don't think anything else is left. Cool then. Any doubts? You can ask right now. Any doubts regarding Proteus or anything regarding the content we've covered so far? The next workshop will also discuss the previous year's problem statement, so you guys have an idea of what you will be of what you will have to implement. So all I can say is that you will mostly be using these ICs in pre-built, okay, and you have to use them to build up the logic that is required from you and solve the problem statement.